to look at. So today we're starting to look at integration of hyperbolic. All of these results are on the formula sheet in some way, shape, or form. But integrating sine and cos is easy because you know sine and cos, sorry, just differentiate to each other, so they also integrate to each other. So sine just integrates to cos x, obviously plus c. Cos integrates to sine x plus c, and tan and sec squared are on the formula sheet. This is the formula sheet. So on your formula sheet, there are some results for integration. So integrating tan, it tells you goes to ln cos x. And integrating sec squared isn't on the integration bit, but if you go to the differentiation bit and go backwards, it tells you tan x differentiates to sec squared, so sec squared integrates to tan. So, plus c. Okay, so the first one is just integrating sine and cos separately. So integrating 2 sine 3x, sine integrates to cos, you need to divide by the 3 in front of the x. So we're going to get 2/3 cos 3x, so the reverse chain rule on that one. Cos integrates to sine, and we need to divide through by the 4. So I get 5/4 sine 4x plus c. The next one, x sine x, is an integration by parts question. U is late, it doesn't really apply here because there's no h hyperbolic, but you can treat it like a trig. So we've got algebra before trig, so we're going to choose u to be x in this case and dv by dx to be sine x. Differentiating the x goes to 1. Integrating the sine x just goes to cos x. You can stick these into the formula. Remember, the formula is on your formula sheet, but the formula says it's u times v, so x cos x, minus the integral of v times du by dx. 1 times cos x, which is cos x. Integrating cos goes to sine, and you plus c on it. I'll go through all these examples and give you time for the u tries. Now, sine squared x will be a similar technique to integrating sine squared x. So integrating sine squared x, you have to turn it into a double angle for cos. Integrating sine squared x, you'll have to turn it into a double angle for cos. So if we write down the formula for cos 2a. Okay, so this is the double angle formula for cos, which you know from single maths. We can use this to work out the double angle formula for cos. So cos 2a equals 1 plus 2 sine squared a, because remember, hyperbolic identities are equivalent to trig identities, except if you've got a sine squared in there, or a tan squared, or a sine times a tan, you need to change the sign on it. Okay, so this has got a sine squared in it, so I've changed that to be a plus, and then it's sine squared there. You can rearrange this to make sine squared the subject. Sine squared a equals a half cos 2a minus a half. Okay, so minus that 1 across and divide by 2. This turns this integral into a half cos 2x minus a half dx, which we can now do. So integrating cos goes to sine, and we divide by the 2. Integrating a half goes to a half x, and c. That's why it's important that your trig integration from single maths is.
Why can you not use the sine squared and do the chain rule?
Reverse chain rule doesn't work on this one because if you were to differentiate like sine cubed, you get a cos on the outside, so there's really more. You can't just divide through by cos x.
Can you never reverse chain rule a trigonometric function?
You can reverse chain rule something like this, because this has got the differentiated bit on the outside. but this one doesn't, so you can't do it with that. Integrating tan squared works the same as integrating tan squared. So integrating tan squared, again, I'll write it up here. So use 1 plus tan squared equals sec squared. And turn this into a sec squared because you know that sec squared integrates to tan. Same for the hyperbolics. So 1 plus change it. Yeah. So the equivalent hyperbolic identity is 1 minus tan squared x equals sec squared x. Because again, same rule, if there's a sine squared or a tan squared, you change the sign on it, which we've got here. But sec is just cos, so we don't change the sign on that one. So the identity we're going to use here, if I rearrange to make tan the subject, tan squared is 1 minus sec squared x. And I can swap that in. I'm integrating 1 minus sec squared x now. Integrating 1 goes to x. Integrating sec squared, you can get it off the formula sheet, but it integrates to tan. And we've got equals c. Final one on this one. So you can use a substitution for this one. If you were going to use a substitution, you could use the substitution u equals cos x. And it would work out from there. The sin x would end up cancelling out. Or you can notice that this is a reverse chain rule. So you can notice, if I write it like this, the outside here, the sin x is the inside differentiated. So the outside came out when you differentiated the original function because of the chain rule. So all I need to do is integrate the bracket, basically. So I add 1 to the power and divide by the new power. By recognition, you can write down this is 6 to cos 6x plus c. Or like I said, you could use the substitution u equals cos x and it will work out the same. Right, we'll go to the answers to these. The first one, get 5/2 sin 2x plus 7/3 cos 3x plus c. Second one, by parts on this one. Choose your u to be x, choose your dv by dx to be sec squared x. Differentiate x gives you 1, integrate sec squared gives you tan. And then you end up integrating tan again, so you get ln cos x, which is on the formula sheet. So it's x tan x minus ln cos x plus c. Over the page, integrate cos squared. So use the double angle formula for cos, which is the same as the double angle formula for cos because there's no sine squareds in it. So it's 2 cos squared x minus 1. Rearrange this to make cos squared the subject and then replace x with 4x in this formula here. So you're integrating a half cos 8x plus a half, which gives you a 16th sin 8x plus a half x plus c. Tan squared 2x, same thing, so use the same identity to turn it into sec squared, so you get 1 minus sec squared 2x. That integrates to x minus a half tan 2x plus c. Finally, this one you can use the substitution u equals sin x if you want, or you can recognize that the cos x came out because of the chain rule, so you can ignore it and just add 1 to the power and divide by the new power on your sin, and you get a quarter sin 4x plus c. And there's 2 more examples on here of ones that you can use kind of equivalent trig methods for integrating these hyperbolic. So this one here, this e to the x cos 2x, it's tempting to try to use integration by parts twice on this, because when you get e to the x sin x or e to the x cos x, you can use integration by parts, and it ends up getting like the original integral, and you bring it back over and stuff. This one won't work because you will get the original integral, but it won't change sign and it will just cancel out. Okay, because cos and sin don't kind of cycle around in plus and negative. So I don't think this will work with integration by parts fine. Instead, what you can do is you can turn your cosh into exponentials and integrate it that way. So if we write cosh in terms of exponentials, so we know cosh x we can write as e to the x plus e to the minus x over 2, and instead of x we've got 2x in, so it's e to the 2x plus e to the minus 2x over 2. All I need to do now is expand this out and bring the half up to the front just to neaten it up a little bit. So I get e to the 3x. And then e to the x times e to the minus 2x gives you e to the minus x. And then it's just a case of integrating these. So integrating e to the 3x gives you a third e to the 3x. Integrating e to the minus x gives you minus e to the minus x. Plus c, you can leave it like that, you can expand it out if you like. So 6 e to the 3x minus half e to the minus x. Okay, so when you look at it and you figure, well, I can't integrate it as it is, but what I could do is turn it into e's, ends up being a bit nice. Final one over the page. So having a look at this, you're looking at it and thinking, can I use an identity for this to simplify it? Well, no, not really. There's no identities that will help you out here. So again, what we're going to try is turn it into e's and see if we can go through that. Okay. So we're going to use the fact that sin x is e to the x minus e to the minus x over 2. Cosh x is e to the x plus e to the minus x over 2 minus 1 dx. I'm going to tidy up the denominator there. So I don't like that it's over 2 inside a fraction. So I'm going to times top and bottom through by 2. And then expand this out. So I've got 3 e to the x minus 3 e to the minus x. Minus e to the x minus e to the minus x. Minus 2, because I times everything through by 2. And collecting up my like terms. So I've got e to the 3 e to the x minus e to the x gives me 2 e to the x. Got minus 3 e to the minus x minus another one of those gives me minus 4 e to the minus x. And that minus 2. And actually everything is a multiple of 2, so I can cancel 2 off. Everything. Okay, I've turned it into exponentials, tightened it up a little bit. Still doesn't look that nice. The next thing I don't like is that there's an e to the minus x on the bottom of this fraction. So I'm going to times everything through by e to the minus x. Sorry, e to the x, sorry, not e to the minus x. Turn it into e to the 2x minus e to the x. I've just written the bottom kind of the other way around, because if I times it through by e to the x, I get e to the 2x. This is minus 2 and minus e to the x. Written it this way around, so you can kind of see it's quadratic. At this stage, yeah, it doesn't look that nice. I'm going to use a substitution. We're going to use the substitution u equals e to the x. So if I differentiate that, I get e to the x. And rearrange this to make dx the subject. Get du over e to the x. Subbing all this in, I can I'm going to leave the top for now, 3 to the x. On the bottom here, I get u squared minus u minus 2. And I get du over e to the x, which is cancelled out that one. And the bottom, I can factorize. You could have factorized it here in green, but I can factorize that to give me u minus 1. So u minus 2, u plus 1. There's a lot of things going on here, a lot of not obvious things to do. What you should be thinking here now is that this is partial fractions. So I can split this up into partial fractions. So a over u minus 2 plus b over u plus 1. Come up with the identity to work out values for A and B, and then substitute in values for U. So if I say U equal -1, it'll get rid of A. Sticking -1 gets rid of A, B is times -3, and if you divide through by that, you get B is -1. And if I stick U is 2 in, I get 3 equals 3A. The B disappears, so you get A is 1. Turns your integral into 1 over U minus 2 minus 1 over U plus 1. Which we can now do. So this integrates to ln U minus 2 minus ln U plus 1. There's no numbers in front of the U's divided through by. You can leave it like that and then sub the back in, or I'm going to put this together into a single ln. So divide those and then substitute back in e to the x, which gives you that at the end. A lot of stuff going on there. But it's one of those where you keep trying stuff and keep. Hopefully this next step will start revealing.